Hello, Farouk here at DirectHub, and for this week, we're going to redo and do some practice questions covering beam determinacy and stability. So I know on this channel, we've done a few of these before, and we did it slightly a different way than what we're about to do today. Today, we will focus on applying the FE Handbook. So remember this, the FE will test how you apply the FE Handbook. They're not expecting us to memorize a lot of equations. They want to test how we apply that handbook and whether we really know how to apply the equations and understand the fundamental concept and also the process and the logic behind those equations. So what we're going to do is focus on applying the FE Handbook to solve these questions. And you might not expect this, you can actually solve these beam determinacy and stability using the FE Handbook. Now less talking, more practicing. So don't forget, you want to pause the video, attempt each practice question on your own, then you can check to see if you got what I got. So you can check your work, but always attempt these on your own. Pause the video, attempt it. If you get it wrong, that's okay. That's perfectly fine. You're going to get some of these wrong, and this is the best way to learn. Making plenty of mistakes and errors is the best way to learn. So make sure you do these on your own. Okay, let's start with this first one. We're told the beam in the figure below is what? So is it A, stable and statically indeterminate to 2 degrees? B is going to be 3 degrees, C is 4 degrees, or D, 5 degrees. Which one is it? So in this case, all of them are indeterminate. So we know that's going to be absolutely true. But now the number of degrees is the one we want to find. This is what they're asking. And what we have is that beam given. So how would we solve this? So you can use what we've done in the past. I'll link that video below. But what I'm going to do is use the FE Handbook. I don't want to memorize nothing. I don't want to memorize. I just want to use the handbook, especially for something like the FE. I want to make efficient use of the handbook instead of like memorizing. Maybe I'll forget. Maybe I'll get frustrated, clouded, flustered, which is very common for such an exam. So we know we're going to use a plane frame. So ignore the truss part. Ignore this. That's not applicable. That's just trusses. Just note the plane frame can be applied to beams as well. And this is what's different. So we're going to say it's going to be for a beam as well. And now we're going to apply these. If this is true, it's unstable. If this is true, it's going to be stable and determinate. And if this is true, it's going to be stable and indeterminate. But obviously in this case, it's going to be true because everything's indeterminate in the answer choices. So we have to have that. And one thing I want you to note here is this. Stability also requires an appropriate arrangement of members and reaction components. So this is talking about, let's say, the external stability of the structure we're looking at. And we will talk about that as we continue at the end with the last two practice problems. Because that one's overlooked and it can be tricky if they're trying to trick you. Usually, sometimes they're not, sometimes they are. So we'll talk about that as well for beams specifically. So now let's go above, and what we're going to say is the following. We will apply what we're given in the handbook. So we will say 3m plus r, and it's going to be a question mark. Is it bigger, less than, or equal to 3j plus c? So now we know each term here, m is going to be defined, if we go down, as the number of members, r is the number of independent reactions, j will be the number of joints, and c is the most annoying one. C is the number of condition equations. So that part is tricky. And we know usually for a hinge, an internal hinge, it depends on the internal moment of 0. What this is saying, let's say for a hinge, you have an extra equation we have to consider, which is like number of condition equations. Think of it as equations outside of global equilibrium, which is some of the forces in the x must equal to 0, some of the forces in the y must equal to 0, and some of the moment must equal to 0. We always apply those 3 equations of equilibrium, global equilibrium. Then what we're going to do is bring in an extra equation, which is condition equations. And typically it's going to be for a hinge, or it can be the pin, where the pin, if you have multiple members connected at the pin, C is also applicable for pin connections or hinge connections as well. So we know in this case, it's the internal moment equal to 0, and some of the moment must equal to 0. And that's going to be the extra equation, because we know there's a moment at a hinge or a pin, and that must equal to 0. And that's going to be the extra condition equation. But we'll talk about C as we proceed and give you an exact way how to find it So you won't have to think too much, especially for something like the FE. So let's go above, and those are defined. So now this is the tricky part for this. If you're applying this method, is the M value, you would think, okay, it's just one member. No, that is not the case. So don't make that mistake if you're applying this. The M value is going to be each member that's separated by the joints. So you have to think of like separating this thing at joints. That's the first part that I would focus on, is that J value. And let's use red for the J value. So we know how many joints are there in this case. This would be a joint. So there's going to be one joint here. I'll put 1. So joints are for red. This is 2. This is 3. And this is 4. Basically at points where you have something change. Usually it's going to be the shear that changes, moment changes, points where some, like this thing just, you know something's going to happen, right? So at 1, 2, 3, so now we can find that J. So J in this case is going to be 4. So we have the number of joints. That's done. Then what I'm going to do is go back to that M value. The M value is going to be where these joints, let's say, are separated. So think of it as we discontinue here, something happens here, something happens here. So we know that this would be one member, and let's call that 1 for a member. This would be one member, another one, and this would be another member. So now we have 1 plus 1 plus 1 gives me 3. So the M value is 3. You have to do it this way. So the M value should equal to 3. Now for the R value, we'll call it the number of reactions, and we're going to use blue for that. So in this case, everything is going to be the external reactions at the rollers and at the fixed end. So we know at the fixed end, we will have 3 reactions. So this thing cannot move in the X. So we have a reaction in the X, equal and opposite reaction. Then in the Y, we have a reaction in the Y, and we also have a moment reaction because this thing cannot rotate. We try to rotate it with an action. There's going to be an equal and opposite reaction, which we call a moment reaction. So we know we have a reaction in the X, we call number 1. We have a reaction in the Y, number 2, and we have a moment reaction, number 3. So we have 3 at the fixed end, and at the roller, we just have a vertical one. So we have, 1, 2, 3, we'll call this 4. We have another 5, and we have one last one, 6. So we're almost done. So the number of reactions is going to be 6, and C in this case is what? So C is the number of condition equations if we have, let's say, an extra hinge, an internal hinge. Usually, almost always, it's going to be a hinge, but sometimes it's like a roller where you have a roller connected to 2 members. I'll make sure to attach a figure describing both of them, but usually, almost always, for something like the FE, it's an internal hinge. Here we have none. So we have no extra equations outside the equilibrium equations. The 3 equilibrium equations we often consider that for global equilibrium. 3, right? So C in this case is not applicable. We have no internal hinge. So we have no extra condition equations of conditions. So this equals to 0, it's out. We don't consider that. So now let's start plugging stuff in. So we do 3M. So M is going to be 3 plus R. R is going to be 6. And do 3J on the right side. J is going to be 4. So we know 3 times 6, 3 times 3 is 9. 9 plus 6 should give us the 15. So we do 15. And 3 times 4 gives us 12. And we know 15 is bigger than 12. So the left side is bigger. And that tells me it's indeterminate, right? As shown here, the left side is bigger, indeterminate. And the number of degrees, you just take the difference. You take 15 minus 12, and it's going to be, in this case, the 3 degrees. So we have 3 degrees of indeterminacy. So that would be that one, and the answer for this should be B. Now let's do this next one. Don't forget, again, pause the video, attempt this on your own, and check your work with mine. So now we're told the beam below in the figure is what? So we're given this beam, we have a hinge, we have a roller, and we have a fixed end. Is it unstable? Is it stable and statically determinate? Is it stable, statically indeterminate to 1 degree, or stable and statically indeterminate to 4 degrees? Which one is it? We will apply the same steps, just more practice. So we know the equation is what? Same one. So let me just write it to be consistent. So we will say it's going to be 3m plus r, and we will say 3j plus c on the right side. So we will check, is it bigger, equal, or less than? So now, we know m in this case, how many members do you have? Remember, you want to note the joints first to make this easier. So we know the joints, which is like the j value. We have one here, 1. This acts as a joint too, like something's going to happen there. Just think of it that way. The shear changes, the moment changes. The moment there is 0, right? Anytime at a hinge, the moment is 0. So this is 2, and this would be a joint 3, and this would be a joint 4. So now we can denote the number of joints is going to be 4. And then we will note the number of members. So this will be member 1. This will be member 2. And this will be member 3. 3 members. Now we can keep going. The number of reactions, we know at the fixed end. So we have 3. So 1, 2, 3. And we have here just the vertical. So this would be 4. And this one would be a vertical as well. So this would be 5. So we have 5 reactions. And the last one is going to be the C value. So now the question is, do we have an extra condition equation? We do, right? We do in this case because it's internal moment equation at a hinge is 0. The sum of the moment at a hinge must equal to 0. So we do have an extra equation, and it would just be 1. It would just C equals to 1. And the best way to remember this always works, is the number of condition equations for, let's say, a hinge or a pin is going to be always arrived at by this equation. You just take the number of members meeting at that hinge minus 1. Number of members minus 1. So the question here, how many members meet at the hinge in this case? How many touch the hinge? 2, right? 2. So the C value, we take 2 minus 1. So the C value is just 1. So if you had 3 members, it would be 3 minus 1. The C value would be 3. If you had 4 members meeting at the hinge, 4 minus 1, the C value would be 3 in that one. So 3 members is 3 minus 1. You get C value of 2. 4 members, it's going to be 4 minus 1. C value is 3. So I hope that makes sense. But this is a good equation to know just in case. Just in case. But in our case, in this, C equals 1. So now let's start plugging stuff in. So we do 3m. M is going to be 3 plus r. So r in this case we said is 5. And we do 3 times j, which is 4 plus 1. So 3 times 3, so we do 9 plus 5. And when you do that, you should get a value of 14. This would be 14. 3 times 4, 12 plus 1 should be 13. And we notice 14 is bigger than 13, right? And that one tells me it's going to be this one. The left side is bigger than the right side. So we have, in this case, 14 minus 13 gives me 1 degree of indeterminacy. So it's statically, in this case, it's going to be stable and statically indeterminate to 1 degree. So that one should be C. So that one is done. So now we have 2 more, and let's do this. And this one is going to be tricky. This one's designed to trick you. So let's do it just how we would normally do these. So the beam below is what? And we want to pick one of these. And note here we have just the external force. They just denote that just maybe to confuse you, or that's just there. Note that's not a reaction, right? That is not a reaction. So what we will say first is we have that classic equation. So we do 3m plus r, 3j plus c, and we will ask this question. So now, how many joints do we have? I like to do the joints. 1, 2, 3. 2, 1. So j is going to be 3. So we put 3 for j. Then we know the number of members is going to be this member. So this is 1. This member, this will be 2. So m is going to equal to 2. And then we know the m, r, j. So we need the r value. R is going to be 3, right, in this. So 1, 2, 3. And this one is just the vertical reactions, 3. And one last thing is going to be C. Do we have a C value in this one? We have no internal hinge? No, right? C is going to equal to 0. That doesn't, so we just eliminate that. So now we do 3 times m, 3 times 2, and we do plus r, which is 3. And then the question is 3 times j, which is 3 times 3. So we know 3 times 2, 6 plus 3 gives us 9. 3 times 3 is 9, and 9 equals to 9. So now we would go above. So if it's equal, it would be stable and statically determinate, right? It's equal in this case, both sides equal. So if that's the case, we would pick B. B would be incorrect. So this is when you have to be very careful. I don't think the FB will go too crazy, but there are two main things we have to check for external stability. How the beam is just given, or how is it set up based on how it's connected to these reactions. So that's going to be external stability that we have to check for. And they kind of denote that here, right? Stability also requires an appropriate arrangement of members and the reaction components. So now, if we look at this one, we have to imagine that we have 3 reactions, and you notice that these reactions are all parallel. They're all parallel. Anytime you see the reactions being parallel, it's unstable. It will be unstable. So we know that the reactions are parallel, and that tells me this will be unstable. And you can like visualize this as, you can even think of it intuitively. You can like think of that force acting at an angle, or try your arm. If you push this, it's just gonna roll, right? It will roll, and it's not stable. There's no resistance. It will have no resistance along the X. If you apply a force, it will have no resistance. And if we do some of the forces in the X, we can't really apply that. So it has no resistance, and this thing will be unstable because all the reactions are parallel. So in this case, it would be A. It's not B. Even though this is true, this is not true because we have to check for the external stability, overall stability. So it would be unstable. So now let's do this next one. And you might probably connect the dots here. This one's also similar to the past one. So we know we're given this, and we want to pick the correct answer. We're still given this magnitude, just the external force that's there, but don't count it as a reaction. So now we do the 3m plus r, 3j plus c, and we will check this. So now we know the j value in this case. We have 1, 2, 3. So 1, 2, 3. And j would equal to 3. How many members do we have? 1, 2. So 2 here and 1. So, well, I'll just denote this as 1 like I'm doing. So 1 plus 1 equals 2. So m is going to be 2. And then we know the r value will be 3, right? So no, it would be just the reactions how we would originally draw them. So it has to be perpendicular for the roller. It's a normal reaction. So we have 1 here, and we have a reaction here, 2, and we have a perpendicular reaction here, 3. Don't break these up into components, right? So you might like make the mistake of doing the x and y components. That would be 2 plus 2, 4 plus 2, 6. That would get you the wrong answer. So we know it's going to be r is going to be 3. Then the number of condition equations, we have no internal hinge. Forget about that. So c equals 0. Eliminate that. So now what we will do is apply that. So we do 3m, m is 2, plus r is 3, 6 plus 3 is 9. And on the right side, 3 times j, which is 3. So this is 9, this is 9, they equal. So since they equal, what would you like do here and go up? It would be stable and statically determinate. But we have to check for the stability, the overall external stability. This is not true in this case. So always, always, always first check for the external stability. And in this one, there's something called, when you have the reactions that are concurrent, meaning they meet at a point, we know that it will be automatically unstable. What does this mean? This means the following. We know that this reaction here, the normal reaction, will have a line of action. So let's just denote it like that. That's going to be the line of action for that reaction. This reaction is just vertical. It will have a line of action as well. So it would just be vertical. And the last one, it would be this reaction. It has a line of action as well. And notice what happens. All of these meet at a certain point. The forces, the line of actions of these reactions meet at a certain point. And let's just call it point O. So that means they're concurrent. So if all the reactions, the line of action of each reaction meets at a certain point, we know they're automatically something called concurrent. So it's concurrent, and this means at the end of it all is when you have, let's say, an external force applied, picture like you hitting this, with these conditions, with these support conditions, what's going to happen is this body acts like a rigid body and it's going to try to rotate. So it is unstable. It will rotate about point O. So it would rotate about point O, so it will be unstable. So to summarize is this is concurrent. So the key word here is concurrent, where all the reactions meet at a certain point, just the reactions, ignore the external forces, and that makes it concurrent. So it will be unstable. It will be unstable. So the answer should be A for that one as well. It's unstable. So there's two main ones, and this is also applicable to trusses as well. You want to check for parallel. If the reactions are all parallel, it will be unstable. And if the reactions are concurrent, meaning they meet at a point, in this case, we denoted it as point O, it will be concurrent and unstable. So don't forget, I do have a full in-depth review course for the latest 2022 Civil FE exam. And this course is designed for those that want to take their studying to the next level. So this course will cover everything you need to know to pass your FE exam. I know nowadays there's this practice exam, there's this practice portal, or there's this textbook. We're not going to worry about none of that. We're just going to focus on this course because it has everything you need to know to pass your FE exam. You're going to learn the right concepts. You're going to test yourself by applying a lot of practice questions, hundreds if not thousands of practice questions that you will get in this course, and you will build the right mindset for this FE exam. You will build the right study structure, the right study schedule, and you will rebuild and regain your confidence to tackle these practice problems and to be ready by exam day. And also you will learn the right skills for something like the FE. This could be like simple calculator skills that you want to absolutely know, because this thing is timed and you want to make efficient use of the calculator. At the same time, you want to make efficient use of applying the FE handbook. So that's a skill we have to know as well. And also certain, let's say, analysis skills, name dimensional analysis, the unit conversions. You will learn all of that. And one last thing is the right resources. So we're just going to focus on the resources we have in our course, and it's your all-in-one solution. You want to make sure you're using relevant FE type questions that are designed similar to the actual FE exam, that will test you in a similar manner and also test the concepts, making sure you're ready by exam day. So if you're looking for something like that, and if you're looking to get serious and take your studying to the next level, just check out the link in the description. And thank you for your practice and for taking the time to watch this video.